So it's my pleasure to introduce tonight's speaker, Dr. Joe Licciardi is a professor at the University of New Hampshire. And I think that it's almost beyond question that Joe is the most knowledgeable person in the world, literally the world expert on Yellowstone and Teton glacial history. And so it is a real treat to have him here. Joe has a BA and a Bachelor of Science in Geology and Geography from the State University of New York in Genesco. His master's and PhD are from the University of Oregon. Joe has worked here extensively, the Andes in Peru, New Hampshire, Arizona, Iceland, has authored many papers, which is what I've been reading every night for the last week and a half or so. Please join me in welcoming Dr. Joe Licciardi.
In any case, thank you all for coming. It's really exciting to be here. And it's really exciting to be able to tell you this story here, where we've done a lot of this research in Yellowstone and the Tetons. And I gave a talk to this group in 2021, and that was, for obvious reasons, remote over Zoom. So it's really nice to be here in person. So what I'm going to do today is I'm going to provide an overview of the glacial history and some climate history too of the greater Yellowstone region, which includes Jackson Hole and the Tetons. And as you'll see, I modified my title a little bit from what you may have seen online. And reason being, it's not really possible to talk about the local history here in Jackson Hole without bringing in Yellowstone. So I have a very long list of collaborators, past and present here. And if I forgot a name, I apologize. As I say, many more. This is we've been working here for quite a long time, and everything that we do is collaborative. So a lot of what I'm going to talk about is the teamwork. And also our funding sources. We've had generous support from the National Science Foundation over the years, as well as the National Park Service and through the University of Wyoming. So here's a pretty picture of the Tetons and these sculpted peaks. As we'll see, a lot of what you see here is the product of glacial processes. And so I'll be focusing on the history of the glacial history here in Grand Teton National Park and in Jackson Hole. But as I said, I'm also, especially towards the end of my talk, going to provide some new information that we know about the glaciation of Yellowstone. So this is the Upper Geyser Basin here, and this is one of the places that we're still conducting active research. Okay. Bear with me here. Not sure why it's not advancing. Okay, here we go. So a lot of what I'm going to tell you here, as I said, the research has been conducted on the glacial history of this region for a very, very long time. One of my primary mentors on glacial geology of this region was Ken Pierce, who passed away a few years ago. And one of the incredible publications that Ken put out in 1979 focused on the northern part of Yellowstone National Park. And this laid the foundation for a lot of future work, including a lot of things that we ended up doing together later on. Ken called this a story in excruciating detail, and it certainly was excruciatingly detailed and complex. So the stories that he came up with can at times be a little hard to follow because they are so complex, but that's what makes it really fun. And a lot of the work that he did was conducted during his time with the U.S. Geological Survey. He did a lot of mapping on horseback. This is kind of I think the mid-late 1960s, doing his mapping on horseback. So I'll be bringing up some of the work that Ken established long ago. Fast forwarding now, though, to 2018, if I can get this to advance. 2018 was a good year for us to put out a lot of new updated information, basically the state of the art of our understanding of the glacial history of the greater Yellowstone region. And there's a professional paper, a U.S. Geological Survey professional paper, 1835, led by Ken, And there was also a review paper that we published in Quaternary Science Reviews. So this consolidated a lot of the information that we have been working on over the years together, as well as a lot of other people who have been working in this area. I found this photo. This was taken by my PhD advisor at the time. This is the very first day that I ever did field work with Ken Pierce. This would have been August 1997 in the Paradise Valley. And that's Jory Clark there on the left, Ken's in the middle, and he is showing us how to recognize glacially polished surfaces on erratics. And so I was a PhD student at the time, and that was the beginning of a really long and fruitful partnership with Ken. If you unfold that cover of the professional paper, this is what it looks like. This is a photo taken from near the Snake River overlook, and we're standing on a moraine, and there's this shadowy depression that's in this photo in the middle foreground. But when you're in Grand Teton National Park, your eyes are almost always drawn towards the mountains. So it's probably not surprising that the first geologists who worked out the history or proposed the detailed glacial history for the Tetons and Jackson Hole thought that all of the deposits that you see in this photo came from Teton glaciers. But we now know otherwise. Everything you see there in the foreground is actually the product of glaciations in Yellowstone, bringing that material to the south, including this moraine ridge that I'm standing on. That's marking what was the southern limit of the Yellowstone ice cap at the time. And that shadowy depression right in front of it is what we call a kettle hole. So that was a place where we had stagnant ice that later disappeared to leave that depression. We ran a trip through Jackson Hole 3 years ago. The Friends of the Pleistocene is what it's called. Some of you, I think, actually were on this trip. And so we were able to present some even newer information. We're always learning. So everything I'm telling you today, of course, is the product of research, but we're always learning new things, including deciding in some cases that what we thought was correct in the past is no longer correct. So, and we'll be running a field trip tomorrow to some sites. So I'm going to bring you into sort of start with the big picture here of the Western US as it appeared during the Pleistocene. So what you're seeing in this map here are Pleistocene glacier complexes and paleo lakes or pluvial lakes, if you will. And then the big ice sheets to the north, the Laurentide and the Cordilleran ice sheet. And there's a lot of dots and symbols on here with isotopes attached to them. That's related to geochronology, and I'll get to that in a little bit more later. But there's the Yellowstone ice cap. It was the largest mountain glacier system south of the great ice sheets during the Pleistocene. And there's a reason for that. So if we zoom in a little bit to that red square, you'll see some pretty major topographic features here. That lowland area that's going through Idaho, southern Idaho, that's the Snake River Plain. And what that does is that acts as a conduit to funnel a lot of storm systems towards the greater Yellowstone region. It is the primary source of moisture, not the only one, but a lot of moisture that funnels through that lowland, and then it encounters this high terrain. And that's outlined in this sort of horseshoe shape. So that's what Ken called the Yellowstone crescent of high terrain, and it's there for a reason. Geodynamically, we have the Yellowstone hotspot. There's a lot of faults that you can see here related to that crustal motion there. The Teton fault is highlighted, and I'll talk about that in more detail later. So the Yellowstone hotspot arrived in its current location about 2 million years ago, a little before that. So we have storms that are being forced up and over this major area of high terrain. And as a result, a lot of moisture ends up getting extracted from those storm systems. So if we look at the map on the left here, that's a precipitation map, and you can see the dark colors there, including at the Tetons. That's heavy precipitation, a lot of it in the form of snowfall. And that cartoon on the right there is showing what's happening here. You're forcing this moist air up and over the Yellowstone Plateau and the high mountain ranges surrounding it. And as a result, you end up producing a lot of orographic precipitation. So that cartoon there on the right is supposed to be showing storm systems being forced up and over the Yellowstone Plateau, roughly along that red line. It's very dry on the other side of Yellowstone because that's a precipitation shadow, again, because of orographic effects. So we have very high amounts of snowfall. We have a large amount of land that's above a level that can be glaciarized, and therefore we have a lot of ice that built up in Yellowstone. So let's have a look at our current understanding of the map of the limits of what we call the Greater Yellowstone Glacial System. So this is a map that Ken and I published back in 2018. And you actually are seeing two ice limits on this map. The red line, and let me see if I can use my cursor. So this line right here that you see extending past the whiter areas, that's the second to last glaciation in this region, the penultimate glaciation, which we call the Bull Lake. And you'll see that the Bull Lake ice was actually larger than the last glaciation, which is in this lighter color, which we call the Pinedale. Those names come not from here, but from the Wind River Range. So what I'm going to do here is highlight the fact that there's this asymmetric pattern of where we see this Bull Lake penultimate ice versus the Pinedale ice. And nowhere is that more dramatic than in Jackson Hole itself. So if we look in this red square here, you can see that the Bull Lake ice pushed about 30 miles further south than the Pinedale ice did. So we're looking at the last two glaciations here. The second to last glaciation in Jackson Hole was huge, much larger than the most recent glaciation, to the point where it filled all of Jackson Hole with ice. So that's pretty dramatic. And the Tetons themselves, they had mountain glaciers coming down the valleys on both sides, but you can see that that's pretty small in comparison to that Bull Lake ice. So I'm going to get back to that in just a moment, but let's talk about the Pinedale glaciation. This is the most recent glacial episode. It's the one we know the most about because it's left behind most best preserved deposits and landforms. So the Pinedale covered about 20,000 square kilometers, if you add all of that up there, not including the ice further south in the Grove Mountain and the Wind Rivers. And it reached a maximum thickness of about 1,100 meters over the Yellowstone Plateau. So that we're talking about a lot of ice, rough calculation, about 20,000 cubic kilometers of ice. But the question, longstanding question here has been, well, so we've got really good mapping control. So we know how big the ice was. We know something about how thick it was, but what about the timing? When did the Bull Lake and Pinedale glaciations reach their maximum extents? And that's where a lot of the work that I've done with Ken and others comes into play. So the technique that we use is called surface exposure dating. There are other ways to determine the ages of glacial deposits, radiocarbon, for example, but that's very difficult to apply to a lot of these deposits because there's not a lot of organic material on the landscape when you have glaciers around. It's not amenable to that. So the way that surface exposure dating works is that we have cosmic radiation that is constantly bombarding the Earth's surface. And that radiation is coming from outer space. So it's galactic in origin. And that's literally coming from exploding stars. When stars explode, they send out a whole stream of atomic and subatomic particles. And those primary cosmic rays, they strike the top of the Earth's atmosphere and they induce this crazy network of secondary nuclear reactions. But importantly for us, that radiation eventually makes it to the surface and it strikes target atoms in minerals and rocks. When those atoms are struck by those particles, primarily neutrons, they break them into two different parts, one of which is what we call a cosmogenic isotope. So those are being produced by the radiation bombarding those rock surfaces. And the isotope that we've used primarily here is beryllium-10, which you can see is produced when a neutron strikes an oxygen atom in a rock-forming mineral. So that's usually in the form of quartz. That's the material that we tend to work with. If we know the rate at which these isotopes are being produced, we can then go out in the field, take a sample from the top of a boulder sitting on a moraine, measure very precisely the concentration of that isotope in the rock, and then it's a simple matter of division. You figure out how long that rock has been on the surface. We're not determining the age where the rock crystallized. We know we have rocks here in the Tetons that are billions of years old, right? but we want to know when that boulder landed on that moraine and melted out of the ice. That's how we're applying this method. And so just a couple of considerations for how we use this method to reconstruct the glacial history. We're using boulders on the tops of moraines that you can see here, and we're relying on those boulders having sat there continuously exposed to radiation since the glaciers receded. And that may or may not be the case. We have to be careful with how we sample these boulders. Some boulders may rotate or they may roll through time. The crests of the moraines themselves may degrade through time, and so that could cause problems. So this moraine here that you're seeing on the left, that's a Bull Lake moraine. It's a lot older than this moraine here that you see on the right, the Pinedale, which is much sharper crested. So we need to think about that. And even sometimes we might get a boulder that gets recycled from a previous glaciation. So that could give us an age that's too old. So there's all these factors that we need to think about. But when we interpret those ages, we are interpreting them as the time that these moraines were essentially left behind. So it's the time when the glacier is pulling away and receding from that moraine. So it gives us the age of what I like to call the culmination of a glaciation. It's when it reached its peak and then melting started. That's how we think of these ages. So let's return to the Bull Lake here in Jackson. One of the first targets for this technique was to look and see if we can figure out when was Jackson Hole completely filled with ice during this Bull Lake glaciation. So we found some really nice boulders. There's a photo of one of them along the southern margin of where this ice was extending even further south in the town of Jackson where we're standing. And we used that exposure dating technique to come up with an age of 150,000 years. So now we have a pretty good precise number. 150,000 years ago, that was when the Bull Lake glaciation reached its peak here in Jackson Hole. And as it turns out, that's true across many other mountain ranges in the western US. What about the Pinedale? Well, the Pinedale, as I said before, we know the most about the Pinedale because those deposits are best preserved. We ended up dating hundreds of boulders all around Yellowstone, and we came up with a lot of ages for what we call the terminal moraines for outlet glaciers that were streaming away from the Yellowstone ice cap. The numbers that you're seeing here around the periphery of that ice cap, these are averages. So each one of them has anywhere between 8 and 10 ages that we're averaging together to get a representative number. And what you might notice here is that these ages are not all the same. They actually are quite different. The oldest ages tend to be in the north and the east, and the youngest ages tend to be in the south and the west. So what that tells us, and this was a really dramatic result at the time, is that these Pinedale outlet glaciers, they reached their maximum extents at different times. They were not in sync. And what that means is the map that you're looking at right now is actually quite misleading because the Yellowstone ice cap never looked like this. It evolved through time. So if we start putting these ages together, we can see that the center of ice mass was actually migrating through time towards those younger moraines in the southwest. And we think that that's because this ice was building towards its primary source of moisture, which I mentioned earlier, those storms coming up the Snake River Plain. And that's what those numbers are in the circles, 20, 18, 15. Those are approximate places where that center of ice mass would have been during those times. So it's younging towards the southwest. Can we try to actually reconstruct what this ice sheet looked like through time using the ages that we have? Well, that turned out to be a really fun challenge. So what you're looking at here is a different way of looking at these ages. These are probability curves, but the same principle applies. We're looking at terminal and recessional moraines over the past 24 to 10,000 years. So that's the timeline there on the bottom. And what you'll see is we can kind of group these into 3 bins, which we called early, middle, and late Pinedale. And some of these moraines, you may notice if you recognize the names, are actually right here in the Teton Range. And those are some of the youngest ones that we have. So when we put all of this together and attempted to show what this may look like on a map, we come up with this. So this is what the early Pinedale looked like in Greater Yellowstone. Ice built up first in the highest mountain ranges surrounding the Yellowstone Plateau, including the Teton Range. But peculiarly, you'll notice there's hardly any ice, if at all, on the Yellowstone Plateau itself. It was only later that that ice cap bloomed, and that happened during the Middle Pinedale. So we now see ice starting to build up over the Yellowstone Plateau itself. And then in the later Pinedale, we see, now you can see this in map form, the ice is building up to become larger and thicker towards the southwest, again, near its moisture source. And there's actually ice that's receding in other parts of the Yellowstone complex at the time. And that's because as that ice grew into a big kilometer-thick dome, it basically formed its own mountain range, so to speak, and then we have a precipitation shadow that formed on the other side of it in the Bighorn Basin. So let's pose the question, can we look at a little more details about how this may have impacted the glacial geology that we see here in the Tetons and Jackson Hole? So I'm going to zoom in to Jackson Hole now for a bit. This map, some of you may have seen, was really the first detailed map of glacial deposits in Jackson Hole, and this was produced in 1930 by Fritjof Fritzell, who was the first park naturalist here. And the different colors that you see there, those are different units. And Fritzell recognized that there was a Bull Lake and a Pinedale glaciation, so that was known at the time. But he attributed virtually all of the deposits and landforms that we see in Jackson Hole to ice coming from the Tetons. As I said earlier, we now know that that's not the case. In fact, what we see in Jackson Hole is almost entirely the product of lobes of ice that were flowing from Yellowstone towards the east and the north. So we now have three phases of the Pinedale that we recognize here in Jackson Hole. And this is the earliest phase of the Pinedale, which is maybe not at all what you might be thinking. The ice was actually coming from the high Absarokas, flowing down the present-day Buffalo Fork drainage and flowing towards the Tetons. Ice in the Tetons would have been around at the time, but it's very unclear what that may have looked like. So we don't have this on the map. But ice was flowing predominantly here from east to west. And in fact, some of it was flowing a little bit towards the north up the Snake River drainage. So that's the first phase of the Pinedale. Later on, we have other lobes of ice that start to become dominant, the Pacific Creek and the Snake River lobes. And you can see from the arrows here that there's a major shift in the direction that ice is now flowing and invading Jackson Hole. And you can also see ice there that's flowing down Cascade Canyon and scooping out what is now Jenny Lake. The final Pinedale phase is this one here. So there's a little bit of ice recession, but again, we have three phases of glaciation here in Jackson Hole, which are related, as you can see, to what's happening further north and east in Yellowstone. This map's a little bit tricky to interpret, but basically this is our attempt to show that the dominance of those three lobes of ice shifted through time. So this red color is the Buffalo Fork lobe. That was predominantly what was filling Jackson Hole with ice earlier on in the Pinedale. And then that shifted to Pacific Creek and then eventually to the Snake River lobe. So we have three glacial lobes that are corresponding to these three glacial phases in Jackson Hole. Each one of these lobes produced enormous volumes of debris, outwash, glacial outwash that was carried beyond the ice margins in glacial meltwater streams. And those form what we see now today as these terraces or these vast flat areas that we see in Jackson Hole. They're not really flat. Technically, they're fans. They have this very slight dip to them. And what you can see with these different arrows here is that they are of different ages. So some of these outwash fans correspond to that early Pinedale phase, some correspond to the middle, and some to the late. So the Pinedale 1, 2, and 3. And you can see that those arrows are not all pointing in the same direction, showing this shifting importance of those three lobes. So let's look at a pretty photo for a moment, one that you've probably all seen before. My favorite photo here by Ansel Adams from the Snake River Overlook. Each one of those flat surfaces that you see there is a glacial outwash terrace. And each one of those terraces is corresponding to a major episode of glaciation. So if we want to develop a chronology of glaciation in Jackson Hole, a glacial history, the best thing that we could try to do anyways is to figure out how old each one of those terraces is. And then we would have a beautiful chronology of glaciation. Well, it turns out that that's not easy to do. So if we look at this map, it gives a little bit more of a picture of these outwash surfaces in the stipple, but we also have places where we have glaciers coming out of the Tetons, forming really prominent moraines. And those moraines are in contact with the outwash. And in fact, we can often determine whether the outwash is above or below or coeval with these moraines. So we can't really date the outwash terraces directly by available means. It's certainly been attempted, but the ages, it's very difficult to do this with radiocarbon. We can't do it with this exposure dating method that I explained earlier. So what we do instead, or what we have done, is we rely on those stratigraphic relationships between the moraines and the outwash surfaces to indirectly date how old those terraces are. That's basically the best we can do at the moment, but maybe someday we'll have a new technique that will come along, allowing us to date those outwash deposits directly. So a really good example of this is at Jenny Lake. So if we look at Jenny Lake here, this is a photo by Michael Collier. Really beautiful photo. You can see these outwash surfaces here in the foreground. Those are those outwash fans coming from those lobes of ice from Yellowstone. The forested enclosure around Jenny Lake, those are moraines, and there are actually quite a number of those moraines. These symbols are telling us how, at least what order these terraces are. So we know that some of these are associated with the middle Pinedale or the Pinedale 2, and those themselves are subdivided into even more stages. I won't go into all those details. Some of them are Pinedale 3. If we look at the Jenny Lake moraines, there's a lot of moraine ridges here, but we group them into what we call an inner and an outer belt, the outer belt being the darker blue. That outer moraine is partially buried by Pinedale 2 outwash. So by simple superposition, we know it has to be older. It had to be there when this outwash buried it. In contrast, the inner moraine abuts right up against Pinedale 3 outwash, so we think they're about the same age. So if we can date these moraines, we can actually then indirectly figure out how old the terraces are. And that's the approach we've taken here in Jackson Hole to come up with our chronology. So let me take you through some of our results. And I don't want to blitz you with too many numbers here, but I'm going to put up a lot of numbers here so you'll see what we've come up with here for our dating efforts here in Jackson Hole and the Tetons. So this is ice coverage here now during the Pinedale, and you can see that the mountain glaciers in the Tetons were all, for the most part, in the southern and middle part of the range, independently contained valley glacier systems. Some of them coalesced a little bit, but then they all get engulfed by Yellowstone ice further to the north, just north of Jenny Lake. So by the time you get to Lee Lake, for example, which is right here, that was covered pretty much entirely by Yellowstone ice, intermingled with Teton ice. That red line there is the trace of the Teton fault, and I'll get back to that in just a moment. The blue lines and the purple lines are the moraines, terminal and recessional moraines for these mountain glaciers in the Tetons. Those are our primary targets for exposure dating. And as I showed, we can also use those ages to figure out how old the terraces are. So this is a sampling of some of the boulders that we've sampled. There's actually a lot more further down as well. We've done a lot of work around Phelps Lake as well. The yellow dots are all moraine boulders. The green dots are further up the valleys, and those are places where we have ice-scoured bedrock. And that's important for us too, because if we date those surfaces, we can figure out how fast glaciers retreated up valley. So I'm going to zoom into this middle part of the range here, where we have a lot of samples in and around Taggart, Bradley, and Glacier Gulch. And I'm going to melt that into the LiDAR. We have full coverage LiDAR, which is a beautiful thing to work with in the park. So you really see the morphology of these big, bulky moraines. And you can see we've targeted the end moraines and also the lateral moraines that are there between the valleys. And one thing you'll notice is that we have samples above and below the Teton Fault, which you can clearly see in the LiDAR as a break in topography. So that means that we can actually, we can start looking at these ages, not just for the glacial history, but for the tectonic history of the Tetons as well. And then you can see our green dots that are further up the valley where we have bedrock ages. This is the kind of boulder you want to find for exposure dating, right? This is what I call this the marshmallow boulder. It's my favorite boulder in the Tetons, I think. And I have a lot of favorites, but this is probably my favorite. It's tall, it's stable, it's got a nice wide base to it. It's very unlikely to have rolled or moved. And it's probably looked like that ever since the ice melted back and it got released from the front of the glaciers. So we get an exposure age from it. This is what we're looking for. Of course, not all of the boulders that we date are dream boulders, but we look for the best boulders that we can find. So this is ice-scoured bedrock up here, up Avalanche Canyon. That's Taggart Lake down there. So this is near Taminaw Lake. And so we have samples from up the canyons as well. And at this point, I should also mention that there's a whole other story to be told from the lakes themselves. And that's work that's been primarily led by Darren Larson, who's back there in the back row. So if you have any questions about the lakes, you can ask Darren. But this is one of the coring expeditions from Delta Lake. And that's the coring rig right there. Darren, I don't think is in this photo, but the person that's on top of the rig there, that's Sarah Crump, who passed away a few years ago, and she is greatly missed. She did a lot of really excellent work here in the Tetons, and these coring expeditions were very successful, and some of this is published, and those are some of the sediment cores from Delta Lake that were extracted. Again, if you want to hear more about that part of the story, you can ask Darren. So back to the cosmogenic dating, the first sequence that we dated was Jenny Lake because we had that really nice interfingering with the outwash surfaces. We get ages of those moraines that are enclosing Jenny Lake that are roughly about 15 to 14,000 years ago. And then some ages up Cascade Canyon, and then Lake Solitude, we have younger ages. So that's pretty cool. So we were thinking, all right, it looks like the terminals here are all about 15,000 years old. That's interesting. And then we moved further south and we started dating more. And a very interesting result came out of this. The boulders that are on those high lateral moraines, those are the purple lines, are actually quite a bit older than the terminal moraines by thousands of years. So for example, at Bradley Lake, the high lateral moraine is almost 22,000 years old. That's an early Pinedale age. Whereas if we look at the moraines further down, they're only 15,000 years. So we missed a big part of the story at Jenny Lake, and we found this out as we did more work further south. So the big conclusion here is that those high lateral moraines are several thousands of years older than the terminal moraines, and we're looking at something that's probably an earlier phase of glaciation, an early Pinedale glaciation. What we think explains this is that in the early Pinedale, those high laterals were deposited, and there must have been terminal moraines at the time, but we don't see them anymore. Maybe they're buried underneath the outwash, or perhaps more likely, that later phase of the Pinedale pushed and overrode them and basically destroyed them because the valleys would have been progressively over-deepened in the intervening time. So it's a very interesting pattern of ages. And if we look at this middle section here, just from a slightly different angle, again, this has been a really nice location in the park to learn a lot. We see that Teton Fault again, cutting those moraines. Well, the moraines that fault is cutting, those are the high lateral moraines, which are about 20-something thousand years old. So what we can do, if we zoom in here, is to see if we can use this information to actually come up with a history, not just of the glacial history, but the Teton Fault. You can see that fault scarp very clearly in these lateral moraines, that really steep step down that you see there. That's the main trace of the fault there at Taggart Lake. And we have ages above and below it, and we have very precisely measured vertical offsets. So if we know the vertical offset and we know how much time has transpired for that offset to have occurred, we can turn that into an offset rate. If we know the geometry of the fault, we can actually turn that into a slip rate, but that's another step. If we just look at offset rates, what we see here is we get a rate of 2.1 meters per 1,000 years for this interval between 22,000 and 15,000 years. And then after 15,000 years, we have a considerably slower slip rate. So there is a suggestion here that we are looking at variable slip rates or offset rates along the Teton Fault that were higher during glacial times and lower during postglacial times. We're certainly not the first ones to extract information about the slip rate. These are some numbers here from a trench that was dug in the Granite Creek area, work of John Bird. And you can see similarly that there are rates that appear to not be constant through time and slower during postglacial times. I'm going to get back to that in just a moment. But let's pause for the moment and just sort of make a list of what we've gone over so far. A couple of key points here. We know from our exposure dating and other information that we have at least 2 Pinedale culminations in the Tetons, and we think we know when those occurred, 22 to 19,000 years ago for the first early Pinedale phase, 17 to 15 for that later phase. And that's coming from primarily from dating of those terminal and lateral moraines. And I didn't point this out properly, but I should have. The ages that we have from the canyons, the bedrock, as well as the work that Darren has been doing in the lakes, show us that we have very rapid deglaciation up the valleys after 15,000 years ago. And as far as the Teton Fault goes, we have some offset rates that we've been able to determine, faster rates earlier in the Pinedale, followed by slower rates in the postglacial times, perhaps having something to do with glacial loading and unloading. So that's where we're at so far. Now, for the last part of my talk here, I'm going to pivot a little bit, but really not that much. And I'm going to pose a research question that we haven't really addressed directly, but it actually is relevant to everything that we've talked about so far. And that question is, when did the Yellowstone Plateau become ice-free? I've primarily been showing you information from moraines that are around the plateau, pretty far from the plateau. So we only really have indirect constraints on when that late glacial phase inevitably came to an end. So when did that happen? And I should also put the question out there, why do we care about this? Well, there's a long list of reasons for why we care, and I'm just going to take you through some of the highlights. One of them is something that we've just talked about. If we have unloading of ice in this area, that is going to change the crustal stress regimes, and it's very likely going to have some impact on the faults around here. And there is modeling work by Andrea Hampel and her group suggesting that glacial loading and unloading in the greater Yellowstone region had an impact on slip rates along the Teton Fault. So what you're looking at here is their modeling results. This map that you see up here in the upper left, that's how they drew their map of ice. And what you can see, hopefully immediately here, is that the amount of ice in the Tetons is really quite small compared to what we have in Yellowstone. And as it turns out, the glacial loading and unloading that may or may not be affecting the Teton Faults is really primarily related to the big ice in Yellowstone and not so much to the ice in the Tetons. They were able to show this with their modeling studies, and so this takes a little bit of time to decipher. But what they're showing here is from about 30,000 years to present, slip rates along the Teton Fault for 3 different places along the fault. Let's just look at this plot right here. When they build up the ice in the Tetons and then they take it away, that's that dashed line right there. So what you can see there is that there's a slight modulation from what would have otherwise been a constant slip rate. And there is a higher slip rate that happens when the ice unloads. But when they include the Yellowstone ice, that's the solid line. And as you can see, that's what makes the biggest difference here on the Teton Fault. So why do we care about when the Yellowstone Plateau became deglaciated? This is one reason why. What we really want to know is, when did that ice unload from the Yellowstone complex, if we want to be looking more closely at connections between ice unloading and tectonic activity on the Teton Fault. Why else might we care? Well, I'm going to skip that because I already showed you that. Ice volcano interactions. It's well known in other parts of the world that if you unload the crust, if a glacier, for example, disappears very rapidly, you could start to stimulate mantle melting and induce volcanism. In Yellowstone, for example, there's very good evidence that when that ice cap disappeared, enhanced volcanism occurred in response. Did that happen here in Yellowstone? The answer is no, it didn't. So until very recently, this was the youngest volcanic unit recognized in Yellowstone. And this is a map from Bob Christensen. And that would have been the Yellowstone Plateau rhyolite about 70,000 years ago. Only just this past year, there's a younger unit that was found in Idaho in the Henry's Fort Caldera, which is 35,000 years old. So that's kind of an exciting thing. But neither of these numbers line up with times that we know glaciers were disappearing in Yellowstone. So maybe there was some mantle melting, maybe there was increased CO2 production that made it to the surface. That's the topic of this paper that I'm citing right here from Fiona Clark, but there was no volcanism. What about the hydrothermal systems? Well, what we see today in Yellowstone, all of the famous thermal features, they had to come to be after the ice was gone. And yeah, there was some travertine that may have formed beneath the ice, but all of the big features that we see in the geyser basins have to be postglacial. And there is some suggestion that if you take ice away very quickly, you relieve pressure and you can cause those hydrothermal systems to light up and become very vigorous and active in the form of hydrothermal explosions. Well, it turns out that the largest hydrothermal explosion that's known in Yellowstone, which is what happened here in the north part of the lake here at Mary Bay, that's right here. It looks as though that explosion occurred very shortly after Yellowstone deglaciated. Are they related causally? Maybe, maybe not. But the thing is, there are a lot of other hydrothermal explosions that occurred long after the ice was gone. So it seems that this story of the hydrothermal systems lighting up, there's more research that we need to do about that, but it appears that we have to think about other triggers for hydrothermal explosions. And speaking of those, these are recognized as the most, probably the most concerning geologic hazard in Yellowstone National Park. Not the supervolcano eruption that everyone hears about, but it's more likely that hydrothermal explosions are going to cause trouble. So in this photo, we're looking at a direct contact between deposits from those hydrothermal systems and till just beneath it. So if we were able to date exactly when that how old that contact is, that would give us a nice timeline for when Yellowstone deglaciated, because ice had to be gone for that center to build up. So we gave it a shot, and we went to the geyser basins and we sampled some surfaces for exposure dating here at Castle Geyser, which some of you may recognize. And well, it didn't work. It's not often that we're motivated to write a paper about complete failures, that nothing went the way we thought it was going to go, but we thought that this was an important story to tell. So we called it a cautionary tale, because if other scientists get the idea that, hey, maybe we should try to date center, at least they're going to have this paper to read about all the reasons why it didn't work. So it's usually we get more excited about publishing the results where things actually did work. But so anyways, we can't do this through dating of center. This is a very recent media release from the explosion, the pretty large Black Diamond Pool explosion that occurred last summer. I don't know if any of you were here for that. I was not. But again, this is an area of active research that may or may not have something to do with glacial loading and unloading. If you're a paleoecologist, you're going to want to know when the ice cap disappeared, because your main interest is going to be studying how vegetation becomes established following a glaciation. So this is work that's been led by Kathy Whitlock and many others, her students and colleagues. And so they want to know when the ice disappeared from the Yellowstone Plateau. And if you're a paleoclimatologist, you want to know when the ice disappeared, because there are very likely climatic reasons for the demise of the ice sheet. And that's driven a lot of the glacial geologic research that has been conducted here in the Western US over the years, including in Yellowstone. So let's see what we know so far here for deglaciation of the Yellowstone Plateau. There are lakes in Yellowstone, and if you drill down into those lakes and you try to find organic material and get a radiocarbon age, you can get a minimum age of deglaciation. And that's been done in many publications, but a lot of those radiocarbon ages, for reasons that are often unclear, are not reliable. Some of them are too old, some of them are too young. What about tephra? Well, here we're on more solid ground. So we have tephra in the greater Yellowstone region from volcanoes that are pretty far away from here in the Cascades. And those serve as time markers. So these are ash layers that are here because of ash that came from very far away. The Glacier Peak ash is particularly useful here. It dates between about 13.4 to 13.7 thousand years. If you can find that ash in lake sediments, then you have a marker, a timeline, and you know, well, that gives you deglaciation ages that can be no later than that age. What about cosmogenic dating? Well, as I said, we didn't have until very recently any ages directly from the plateau itself. We were relying on ages from moraines that were around the margins of the ice cap, presuming that the plateau ice had to have disappeared sometime after those moraines formed. But that's indirect. A couple of places where it's been particularly important where we have ages that give us some constraints. Some are right here in Jackson Hole. We have an age of about 15.5 for the culmination of that Snake River lobe that I showed you earlier. And so the plateau still had to have a lot of ice on it when that moraine formed in Jackson Hole. It had to have deglaciated sometime after 15.5 thousand years ago, but that's not a very precise constraint. In the north, we can do a little better. We have some ages on moraines that are associated with stagnation of plateau ice. And I'm going to zoom in to this area here, showing these moraines near the town of Gardner in Montana. There's this moraine in particular called the Deckard Flats moraine that's outlined by that dark blue line. If you follow the crazy sort of path of ice coverage during Deckard Flats time, you'll see it's pretty patchy. And we know that that moraine formed, or it had to have formed, when ice on the plateau was on its way out, if not gone. Unclear, but that 15.1 thousand year age of the Deckard Flats moraines was our best constraint until recently on the deglaciation of the plateau. There's also a flood bar that's shown there in that little red dot, and I'll just show you a picture of that in just a moment, but this is what the Deckard Flats moraine looks like. We have a pretty nice exposure age from this, 15.1 with some uncertainty. This is work that I did over 20 years ago, so we can do better now if we were to redate it. But I'd rather date new moraines rather than old ones. And then there's the flood bar. Now that flood bar represents a major outburst flood that broke through the Deckard Flats limit. So again, ice on the plateau, very likely, though we can't prove it, was probably gone by the time this flood occurred. And so we have an age of 14.4 thousand years. But again, this is not very satisfying because it's not from the plateau itself. So the last few slides here, I'm going to show you what we've learned from the plateau. We now have finally gotten around to collecting boulders that are on the plateau itself, glacial erratics. The exposure ages of those boulders should give us a more direct constraint on when that ice disappeared. How do we find these boulders? Yellowstone is a really big place. Fortunately, we have these beautiful, detailed, superficial geologic maps, many of which were published in the early 1970s by USGS researchers, including Ken Pierce, who's on a lot of these, and Waldrop. And on these maps, there's an example of one of these maps. They're works of art, really. But they also tell you where all the boulders are. So the little asterisks, which you may or may not be able to see, are labeled. And not only that, the lithologies of those erratics are noted. So this is very useful information. Fast forward, we have now digitized, I didn't do this, someone took a lot of time doing this. They digitized the locations of all of these erratics. So you now can look up the locations yourself with this online geology of Yellowstone map. All of those dots there are erratics. We've been focusing our efforts here in the geyser basins. And so zooming in there, we now have LiDAR coverage, finally, for all of Yellowstone National Park, as we've had for a while in the Grand Teton. That's opened up a lot of possibilities. At the moment, we've dated 6 erratics on the plateau. So I don't want to make you think they're super easy to find. Some of them are, some of them aren't. But 6 ages is where we're at. 3 of them, the blue dots, we've dated with beryllium-10 exposure dating. Again, that's from quartz. And the yellow dots, that's another isotope, chlorine-36, but the same principle applies. So those are our sample names. And these are the boulders. So we've got some really nice boulders, all of which have this beautiful glacial working and smoothing associated with them. So these are boulders that were pushed around by the ice and eventually released. In theory, the ages of these should tell us exactly when, or close to when, plateau ice disappeared. So without further ado, these are the ages. This is all unpublished. I'm in the process of trying to write this paper. And these ages came out pretty nice. So we have a pretty nice clustering of ages, and they seem to make good sense. If we look at only the chlorine-36 ages, they average around 14.7. If we look at beryllium only, 14.3. If we throw them all together, we get an age of 14.5 thousand years ago. That makes a lot of good sense based on what we had done earlier with indirect dating of the deglaciation of the Yellowstone Plateau. And it matches up pretty nicely with some of the ages that we get right here in Jackson Hole for the time of mountain valley retreat in the Teton Range. So we're looking at what's emerging as a regional picture of ice disappearing around 14,500 years ago. So that's pretty exciting. Now, the other part of the story, and I'm not leading this part, is the provenance of these erratics. In other words, where did they come from? If we can combine the exposure ages that we have from these boulders with information about their transport path, where they actually came from, then we can actually start to reconstruct former ice flow directions and patterns through time, which would be a really exciting new level of detail in our understanding of the glacial history of Yellowstone. So how do we do this? Well, one way, the obvious way, I guess, is to look at the lithologies of those boulders and see if we can trace them back to an outcrop. Some of the lithologies are distinctive enough to do that. Many of them are not. Yellowstone is famously full of rhyolite that all kind of looks the same. So that's not going to help if you just, all you know that is that it's rhyolite. But you can also look at geochemical evidence and dating of the erratics, and that's going to allow you to more confidently match them back up to their source outcrop. And we have some preliminary results. So I'll just share this one because it's a pretty fun story. This is one of the boulders that we exposure dated at 14,000 years. And we have uranium-lead dating that is very confidently telling us at this point that this boulder came from the Beartooth uplift. It's really the only place it could have come from that makes sense with the age that we get from it, as well as its geochemistry. So let's see where that is on the map. That boulder is where you see that blue dot. And the Beartooth uplift is circled in red. So the question here is, how did that boulder get to the lower geyser basin based on what we see here with the evolution of ice from the early to the middle to the late Pinedale? Can we somehow explain how that boulder got nudged and pushed and shoved and dragged to its current location from the Beartooth uplift to the lower geyser basin? Well, that's pretty tough to do. It couldn't have happened in early Pinedale time because there wasn't even ice there, so that doesn't work. What about middle Pinedale time? Well, that doesn't work either because we have ice that's starting to flow to the north instead of it's flowing in the wrong direction to explain where that boulder is. Late Pinedale, maybe. But what really is probably happening here is that we have to remember that I've told you that an overview of the last 2 glaciations that we know something about here in the greater Yellowstone region. But over the Quaternary, how many glaciations have we had here in this region? 2, 3, 10, 20? More than 20, right? So if you imagine these ice caps coming and going 20 plus times, we can then maybe start to put together a story that might make sense for how that boulder got there. So it's a very fun puzzle to work on, and we are doing this for all of the other boulders that we've sampled. And so that's work in progress. But I'm going to leave you with a summary here for this new work on mostly unpublished, on plateau deglaciation. And so we can say, first of all, that our ages are giving us a pretty good number, now a more direct number for deglaciation of the plateau around 14.5 thousand years ago. And we have nice consistency with our previous information and dating from places that are quite far from the plateau, including the Deckard Flats moraines, as well as the Snake River low moraines that we've dated down here in Jackson. And we still have a lot of work to do with our provenance to figure out where these boulders came from, but we're really excited for this to unveil a lot of heretofore unknown information about the glacial history of Yellowstone. So I would say stay tuned for more information on that part of the story. And well, as I said, we have a lot more, we always have more work to do. We never finish anything as scientists, right? It's just always a work in progress. So this is what we got right now. So I'll leave it at that, and I'll be happy to answer any questions you might have. Thank you.
When you were dating the full length glaciation.
Yeah.
Had samples of around Red Top Meadows.
Yep.
Did you sample any on the other low east of Mountain?
We sampled in Red Top Meadows and around Mosquito Creek. There were a couple of different ridges that we targeted. It wasn't easy to find those boulders. We would have, with exposure dating, it's always the more the better. And some of those boulders came out too young. We think that that's because they've been around a while and they probably eroded or maybe overturned. It's much more likely for Bull Lake for that to be a problem than it is for Pinedale. But suffice to say, we didn't walk the entire contact. We covered as much ground as we had, and we came up with what we felt was a pretty good collection of boulders. But as I said, always more work to do. Maybe someday we'll go down there and try to find a few more. Yeah.
To what degree is what we see in that picture the result of glaciation as opposed to other forms of mountain building and erosion?
Yeah, I didn't say a whole heck of a lot about the Teton Fault, but the mountain topography that you're seeing here, that's a whole other story. That, of course, the final sculpting that we see, the jagged peaks, the U-shaped valleys, the troughs, and all of that, that's glaciation. But the mountains themselves they're a tectonic feature, primarily related to uplift on the Teton side of that fault, and then down dropping on the Jackson Hole side, with much more down dropping than uplift.
Were the glaciation causing significant changes in the middle altitudes there? Were they taking a lot of?
Well, so yeah, I mean, if I'm understanding your question correctly, the Tetons were not completely covered with a dome of ice. So there were a lot of peaks that were protruding above the ice. So a lot of the topography that we see there, like the Grand, for example, that's not glaciation, right? That's mass wasting and other non-glacial processes, which of course have been operating pretty vigorously on this landscape for the past 15,000 years at least, right? But the broader picture is that the Teton Fault initiated quite a long time ago, 5 million, let's say. And we've had, again, many glaciations coming and going during that time as the range has been tectonically building. So there's a lot we don't know about what it may have looked like early on. But what we see today in the Tetons, the dramatic scenery that you see there, it's a tectonically built mountain range that is polished and sculpted by glaciers. And there are some places that you'll see along the range front that are not glaciated. They were between valley glaciers. So there's some little gaps here and there where we're really looking at non-glacial processes.
During the Bull Lake glaciation, about how deep might the snow and ice over the town of Jackson be, or in the middle of the valley? And also, has there ever been, do we know if there's ever been a time when the ice cap of Yellowstone during a period of previous glaciation was connected to the glacial sheets further north? I've heard that, and I've heard, I guess, as an aside to that, there's there's stone that they now know has been pushed south over the period by glacial sheets by, up to hundreds of miles or 100 miles or more by successive sheets of ice?
There's a lot of good questions. Let me see if I can take. Sorry, yeah, let me take the first one. The first one that you asked is, how thick was the ice here in Jackson during the bull lake? Yeah. So, all right, so town of Jackson is right here. The limit of ice in Jackson was roughly about as high as the top of Snow King Mountain. Yeah, and so the relief between the top of that mountain and the town of Jackson, that's how thick the ice was here. But it went a lot, it wrapped around Snow King. So that's how that ice ended up much further south, like you see here in the map. And the contours that you see there on the Bull Lake, which I didn't point out earlier, give you a sense of how much thicker the ice became as you were to, if you were to be walking up that ice at the time towards Jackson Lake. And then ultimately all the way to the Yellowstone Plateau, where we don't know how thick it was, but based on how thick the Pinedale ice was, it was probably at least 1 kilometer thick, maybe even thicker, because as you can see here, the Bull Lake was a larger glaciation in this part of the system. Now, your other question, let's see.
Connecting with ice cap?
Yeah, to the north. Well, there are a number of mountain ranges north of Yellowstone that had their own independent ice caps. The Beartooth area, that was a huge amount of ice. And the terminal moraines for the Beartooth ice, you can now see those along the northern front of the Beartooth, places like East Rosebud and Stillwater Canyons. As far as I know, the ice never made it further north than there, even during Bull Lake time. In fact, the Pinedale was larger than the Bull Lake in those canyons.
But going back to the beginning of the Pleistocene?
To anyone's guess.
All right.
So if we go back millions of years, that's out of my wheelhouse. So we'd have to start thinking about what topography may have looked like. The Yellowstone hotspot itself arrived in its current location about 2 million years ago. And as I said in the very beginning, that has a lot to do with why so much ice built up in Yellowstone in the first place. So there's good reason to believe that there wouldn't have been much ice there before the arrival of the Yellowstone hotspot.
In Teton Valley,
Yep, Idaho.
are there any terminal moraines?
Yes, there are. So this right here, that's Teton Canyon. And that red line right there, that's a Bull Lake ice margin. We've actually dated that. I don't know if I put the ages up. And then that's the Pinedale limit. So the Bull Lake was much larger than the Pinedale on that side of the Tetons. But the issue, and this is another example right here, it's true also in Darby Canyon. I should probably draw that in, and this is Fox Creek. But as you may know, in Teton Valley, there are something like 100 or more, maybe 200 meters of fill, of loess, and that has buried the termini of the Bull Lake moraines. So you don't see that terminus anymore. It's completely buried. In fact, if you walk down the crest of the Bull Lake moraine, it just basically you're just grounded into the flats around Driggs, and we don't see those. The Pinedale terminal moraines, those are more or less intact. But yeah, those glaciers were actually larger on the west side of the Tetons, again, probably because of orographic influences. That's where the moisture is being pushed up, and there's more snowfall over there. Yeah, but that's been a whole sort of part of this project we haven't published on much. It's been a lot more difficult to find good landforms and good boulders to date over there, but we have ages from some of them, as well as some work that we've done in the Alaska Basin, which is connected to the glaciations further down valley in Teton Valley. Yeah, it's a fascinating place to work.
When you say talking about flowing, how fast is that? And
How fast?
glacier flowing, yeah.
Slow.
Yeah.
Let's see. Fastest glacier in the world is the Jakobshavn Glacier in West Greenland, and that moves, let me think, kilometers per year. So if you're not going to see it happen, you'll hear it happening. You'll hear the cracking and the fracturing, but Gosh, I should have a number in mind for like how fast a typical glacier moves, but it's not very fast. Glacially paced. But now I'm gonna have to look this up, and I need to have a number ready if I get that question again. Sorry, I don't have that right off the top of my head. Yeah.
In the Yellowstone Plateau, are there any places where there are peaks high enough where like cirque glaciers emerge during deglaciation? And have you dated any of those? I know it's the closest cirque glacier to the.
Oh, that's a really good question. There, sorry, I have to hold this correctly. So the plateau is, it's pretty flat, but then you have some mountains like the Washburn Range, for example. And a lot of the critical evidence for shifting ice flow patterns comes from those high peaks where we see cross-cutting striations, for example. But as far as cirques go, that entire area was inundated with ice. And so this is a classic question in glacial geology, including where I'm from currently in New Hampshire. When do the cirques form? Do they form before the ice sheet? Do they form after ice sheet deglaciates and they're lingering remnants? We think, for example, in the White Mountains of New Hampshire, the cirques formed probably before ice sheet engulfed the entire presidential range. And I would imagine that same principle probably applies in Yellowstone as well. We would imagine cirque glaciers forming first as we have nevation hollows and then cirques and then cirque glaciers. But then the whole thing gets overridden with an ice cap. So that's going to modify that cirque form. So there are cirque-like forms in the Washburn Range. They're probably, if I were to speculate, they're probably relict landforms from early in the Pinedale prior to being completely engulfed. And they're probably also being modified by postglacial erosion, which can sometimes look very cirque-like. But that's a great question. It's actually a topic of active research in a lot of glaciated regions around the world, is this question of the sequence and the timing of cirque glaciation versus ice cap glaciation and then deglaciation. It's a long way of saying I don't exactly know the answer to your question, but it probably requires a lot more research to think about that in more detail. Darren.
Great talk. I have a question for you.
Okay.
Follow up on the plateau.
Yeah.
How confident are you in the geometry of the ice cap during the early Pinedale?
Oh.
Constraints on the western central margins of that early Pinedale. And I guess as a follow-up, do you think some of your more recent results from these high laterals in the Teton Range dating to that time period, shedding more information or more light on this?
Yeah, great question, Darren. Thank you for that. I would, sorry?
Repeat the question, please.
Oh, I'm sorry. I keep forgetting to do that.
Question.
Okay, so the question is, how confident are we in our ice reconstruction for the early Pinedale in the greater Yellowstone region? And based on our new results from the Tetons showing that those high laterals are in this early Pinedale phase, could those ages and landforms shed more light on allowing us to maybe refine our reconstruction of the early Pinedale? I would actually say this may seem strange, but for these three phases, I think we probably have somewhat more confidence in some of the details of the early Pinedale than we do for the middle Pinedale. The middle Pinedale is pretty tough because a lot of that got overridden by the later Pinedale, but some of these early Pinedale moraines, especially the ones that are in the north and the east, did not get overridden. And so we also, as far as the reconstruction showing no ice on the plateau, we feel pretty confident about that based on ice flow patterns that are reconstructed from striations, cross-cutting striations in mountain ranges that are fringing what would have been the plateau. And not to get too deeply into it, but the other reason why we're confident that there was no ice on the plateau is a glaciological constraint. So if you look at what would have been required for glaciation, the equilibrium line altitude, what that should have been or would have been based on our reconstructions of the early Pinedale and the Beartooths and the Absaricas, for example, that would make it very difficult to explain how ice could have survived on the plateau. It would have been below the snow line. So that's a partial answer to your question. As far as the high laterals and the ages that we get in the Tetons, that's really intriguing because we never suspected that we were going to see anything from the early Pinedale in the Tetons. The expectation was that the terminals were 15,000 years and that's the end of the story. Now, we think that those really old high laterals in the Tetons are likely to correspond to the early phase of Pinedale glaciation with that ice slope coming down the Buffalo Fork drainage. That's the only part of the Jackson Hole sequence for which we really don't have any good age constraints. And that's because this was not a moraine-dominated system. The evidence for this early Pinedale Buffalo Fork lobe is in the form of vast amounts of outwash. And we'll see some of these moraines for those of you who are going to go on the trip tomorrow. Most of them are buried and have no boulders on them. So we don't have any direct ages on this Buffalo Fork invasion of ice. The high lateral moraines, which are not being shown in this photo, though, they probably date to this era. And there is some suggestion from radiocarbon ages in Antelope Flats that have been generated by Glenn Thackeray and some of the trenching work that they've done out there, that there's ages that are in that era that seem to suggest that the Buffalo Fork outwash dates to around this sort of 20-something thousand year old time period. But, you know, we would love to have been able to date this Buffalo Fork incursion into Jackson Hole directly. We walked every moraine that's out there in Antelope Flats, and believe me, it's like they're out there. You won't see them from the highway, but we looked at pretty much every boulder and cobble, and it's just all small stuff. So I didn't feel comfortable exposure dating it. And we can't exposure date the outwash. So I don't know when we're going to crack that, but we're going to keep trying. But great questions.
I'm wondering if I remember correctly from your talk that 15,000 years ago, the thickness of the ice was a kilometer. Is that correct?
Yeah, we don't know exactly when the maximum thickness occurred, but we do have good evidence for what we think of as sort of the late blooming Yellowstone Plateau ice cap during middle Pinedale time. And again, this is all very uncertain over here, but we have very good evidence for ice flow here in the Washburn Range, showing that the ice was actually thick enough to be flowing up and over Mount Washburn at the time. So it had to be pretty thick. And again, if you apply glaciological reconstructions and you use ice flow laws, for example, you can predict how thick the ice had to have been in order to override that mountain range that's sitting there north of the plateau. But as far as the ice reaching its maximum thickness in middle versus late Pinedale, we think there was probably about a 3,000 year period where the ice was quite thick, between approximately maybe like 17 to 14,000, or well, it would be less than 3,000 years. Yeah, sometime middle to late Pinedale, but we don't know exactly when.
That was more of my question. If you know that the ice was gone by 14,500 years ago, to me, at least with that map, which was fuzzy, was really, really rapid. And so I was curious.
Yeah, very rapid.
The theories about the deglaciation was so rapidly occurring.
Okay, I'm going to remember to do this time for the Zoom folks. So the last part of the question is, what explains the very rapid deglaciation of the Yellowstone ice cap, given that it was over a kilometer thick and seems to have disappeared very, very rapidly? That actually, there's a pretty good explanation for why that is a likely scenario. And again, it's based on climate and glaciology, but the plateau, this ice cap had a pretty low profile to it. So it was this very broad sort of lozenge shaped ice mass. And the snow line for that ice cap must have been around the margins, close to some of the outlet glaciers. I'm trying to get my cursor here. So the ELA, if you will, that's basically the snow line, divides that glacier into an accumulation zone and an ablation zone. And when the climate warmed around 15,000 years ago, not just here in the West, but in many other parts of the world, that snow line would have risen to the point where it would have put the entire ice cap into the melt zone. And as soon as that happens, the ice cap is going to respond by melting very, very rapidly. That's very unlike what we would expect for a mountain glacier, a valley glacier, for example, that starts at very high elevations and has this sort of narrow path, and then it spills into the valley as a Piedmont glacier. For those glaciers, they're more resilient to rises in snowline. But for ice sheets and ice caps that have that low profile to them, you can put the entire glacier into the melt zone by raising the temperature by not that much. Yeah. So very, very sensitive to climate when you have that kind of ice sheet geometry. It's a good question. Yeah.
Hydrothermal geyser activity under glacier or at any point, do you think there can be evidence or activity melting it or even happening at all?
Okay, great question. So sorry, was there?
Just
Yeah. So the question is, can hydrothermal activity occur beneath an ice sheet, and are there any deposits or any evidence for that having happened in the past? That's a great question. And so the answer is that, yeah, it is possible. So there are some deposits around here in Paradise Valley that are travertine deposits that are thought to have at least been subaqueous, which is more likely than, well, if you have hydrothermal activity beneath an ice sheet, it's going to create meltwater, right? And so travertine can grow subglacially if it has a subglacial meltwater vault to grow into. And there are deposits in this Paradise Valley area that are suggestive of some travertine formation that may have been subglacial, but the expectation is generally the opposite, that you would expect travertine and other hydrothermal deposits to be primarily forming postglacially. The travertine that we see in the geyser basins here has recently been dated pretty precisely by Lauren Harrison, a colleague of mine, and other USGS scientists. And the oldest travertine that they find is around 13,500, not quite 14,000 years old, which suggests that that travertine really didn't start forming until the ice was gone. So the general expectation is that you're looking at subaerial travertine formation with those springs, but it can happen if you have meltwater beneath the glacier. Turn this over to you.
Yes.
Okay, thanks, Mike.
Thank you very much, Joe, for an amazing experience.